Today we are going to look at finishing off chapter 7. In particular, we're going to be doing the last topic in chapter 7. Its heading is complex numbers. So let me give you a little bit of background. If I asked you to solve a very simple equation for what values of x is x squared equals 1, there are actually two solutions. The most obvious one is x equals 1. And if you check it, x squared, which is 1 times itself, is 1, and that works. Of course, there is a second solution that sometimes people forget about, and that is that x could be negative 1. And just to show you that that also works, x squared would mean negative 1 squared, which is negative 1 times itself, and yeah, that equals 1. So in this particular example, there are two solutions. And those solutions are x equals 1, and the other solution is x equals negative 1. So imagine a mathematician came up with this problem. He's trying to solve the equation x squared equals negative 1. Now the logic would be that there is no solution. But actually, if we're being a little bit formal about that, what we really mean is there is no real number that is a solution. And a real number for most of you is all the usual typical numbers like 1.5 and 0.3 and the square root of 7 and so on. Any number essentially that you could draw a number line and somewhere in that number line you could put a point that would represent the particular value that you've got. Those are called real numbers. And for a long time, that was kind of the end of the problem. And then they started thinking a little bit more deeply, and they said, okay, we accept that there isn't any real numbers that look like this, where that is true. But suppose there's another number system, one that we haven't created or discovered yet, which was able to solve this problem. Well, if you were going to be able to do that, x would have to be the square root of negative 1. And so they decided that they were going to create a new number, and it's given the letter I because it's easier to write I than it is to write down the square root of negative 1. And this new number I is going to be the genesis of the start of this new number system, which is going to be called the complex numbers. A normal complex number, let's call it Z, is going to be made up of two pieces, A plus B I, where A and B are real numbers. So, for example, 3 plus 2i is an example of a complex number. And that's the name that we give to these new special numbers. We call them complex numbers. So 3 plus 2i is an example. 4 minus 5i is an example. 7i on its own is an example. And actually, 3 on its own is an example of a complex number. So what that means is that the numbers that we've been used to for all your life, probably, the real numbers, like 3, for instance, is just one small part of the bigger world of complex numbers. So real numbers is a small group of numbers inside an even bigger group of numbers called complex numbers. And we have some names that we give to things. So when you have a complex number, for instance, like 3 plus 2i, the number 3 is called the real part of the complex number. And the number 2, not 2i, not I, just the number 2, is called the imaginary part. And what we're going to deal with in this section is essentially how to work with this new number system, how to add them together, how to subtract them, how to multiply them. And we won't go into dividing, but we'll do add, subtract, and multiply, which is quite a lot. We'll look at how do you actually create them from questions or numbers written down as weird square roots as well. So that's our goal. So here's our first one, which is which of these numbers, right, can be simplified down to a more typical complex number. So let's take that guy. Now they both have square roots, but each of these square roots can be simplified. So that's what I'm going to do first. 81 is a perfect number. Its square root is 9. This guy here is going to be split. And you're always going to split it the same way. You're going to split it as the number part times -1. So if you ever have a square root of a negative number, as we have here, that is going to generate one of these guys here. It's going to generate some version of I, some imaginary part of the answer. So we're going to call it 49 times -1. And then that can be split as the square root of 49 times the square root of -1. And the square root of 49 is a nice number, it's 7. And that guy there, we will call him I. So this number, just calling it a vague term number, is actually the complex number 9 plus 7i. Now, if you had the exact same two square roots, but you had that, a common mistake is people think that this negative will cancel out that negative and we'll end up with the square root of 81 plus the square root of 49, which is just 9 plus 7, we get 16. That is not how this is going to work. A negative outside the square root does not interfere with or join a square root that has a negative inside it. So they are totally separate. We're not going to mix them. So this guy is going to be 9. Just like we did up here, it's going to be 49 times -1. I can then split that as the square root of 49 times the square root of -1. That's a nice number, so you get 7, and that is I. So you can see that there isn't really too much difference between them, right? A plus gives you a plus, a negative gives you a negative. And that is the gist of how to convert square roots into their equivalent complex number. So if I gave you as an example, question 4, and you were asked to simplify this square root, just a single square root, you're going to write it as 64 times -1. That in turn is going to be the square root of 64 on its own times the square root of -1 on its own. And that is in turn going to be called 8. And that guy's I. So there is your answer, 8i. Let's add a multiple at the front and see if we can make it a little bit harder. Let's suppose we take, for instance, a version of question 5. And we ask you to do 5 times the square root of -100. So what we're now going to have is 5 times, and the -100 is going to be 100 times -1. So that's going to get me 5 times the square root of 100 times the square root of -1. The square root of 100 is a nice exact value, it's 10. And 5 times 10 gets you 50. And the square root of negative 1 gets you I. So there we go. This 5 times the square root of negative 100 is, not surprisingly, 50I. Now, you're not always going to get nice real and imaginary parts, right? In this case, 50. It's a nice value. You could get the square root of negative 20. So I'm going to begin with 20 times negative 1. That's the typical split. Now the square root of 20 times the square root of negative 1. And now you're going to have to think back to simplifying square roots like 20. And that has to get broken down as a square number 4 times what's left, 5. And that guy is just an I. And that guy gets you 2. That guy gets you square root of 5. And there's your I. And so your answer to the simplified version of the square root of 20 is 2 square root of 5 I. Let's try question 12. 7 times the square root of negative 117. Now you're looking at that guy, you're probably going to say, I'm not sure if 117 is going to be anything interesting. I'm pretty sure, if you can check, which I'm about to do, that it's not a perfect answer, right? If you try, well, let me split it first. 7 times the square root of 117 times the square root of negative 1. If you try to find the square root of 117, nothing good comes out of it. So we would be looking at our squares, so 2, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, and 9 squared, and so on. So I'm trying to find something, one of these numbers that divides 117. So if you start at the top and work your way upwards, that's the right way to do it. 117 divided by 81. I don't give this much hope. No, it doesn't work. So 117 divided by 64 is a non-starter. If your number is odd, like 117 is odd, even guys will never divide it exactly. So the next one is 49. That didn't work. So 117 is going to get divided not by that because it's even. 25, I know that's not going to work, but for completeness, there we go. 16 is not going to work. I'm going to do 117 then, divided by 9, and we finally got it. It was 13. So that means it's 7 times the square root of 9 times 13 with a 9. And that guy gets you the square root of 9 times the square root of 13 with an I. That guy gets you 3, so it's 7 times 3. And 7 times 3 gets you 21, square root of 13, I. And now we can say that we have simplified the original ugly square root into a complex number. Hopefully you're still with me and you're comfortable now about simplifying square roots that are on their own. If we continue that a little bit further and we get to questions like question 13, where you've got 14 plus the square root of negative 112. Well, I don't need to do anything with 14. It's totally fine, right? I'm going to rewrite this as 112 times negative 1. So that's going to be 14 plus the square root of 112. Square root of that guy is going to get me I. So I just need to focus on 112. Right. here is a choice. If you start with 112 and do 81, it doesn't work. I'll try 64 now. Doesn't work. I'll try 112. And I'll try dividing it by 49. That doesn't work. I'll take 112 and divide it by 36. And that doesn't work. I'll take 112 divided by 16. There we go. So it can be written as 16 times 7. So it's going to be 14 plus the square root of 16 times the square root of 7, I. And the square root of 16 is 4. So you get 4 root 7, I. And so we are finished. 14 plus the square root of -112 simplifies down to that. The next question is a little bit different, just a little bit enough to perhaps cause issues. It's 6 plus 4 square root of -45, which is pretty normal. And then you have this whole lot over 3. So what I'm going to do is I'm going to separate that first. Into that guy over 3 plus this guy over 3. And that guy can become 2. And this guy here is going to be 4/3 times the square root of 45 times -1. Square root of 45. I. Now I'm looking for 45. The best one actually ends up being 9. So it's 9 times 5. I. So it's 2 plus 4/3 times the square root of 9 times the square root of 5. I. And that becomes 4/3 times 3 square root of 5. I. These cancel. We get our final answer, which is 2 plus 4 square root of 5i. That is a simplified version of that. So far, so good. And let's move on and do one last one of this type. Let's do question 17. One of them like question 17. 8 take away 5 square root of -12 all over 12. Now that will split as 8/12 take away 5/12 square root of -12. That simplifies down to 2/3. Take away that guy, and the square root of -12 is 12 times square root of -1. So we have that. Square root of 12 can be written as 4 times 3. That's going to become the square root of 4 square root of 3 with an I. That's times 2 square root of 3i. That cancels partially with that to leave 6 in the bottom. And our final answer is 2/3 take away 5/6 square root of 3i. That fella is the final result. So if I gave you a square root that looked something like 13 or maybe even something like 17, I hope you've got a good idea of how you would approach solving the problem and essentially simplifying it. So now we're going to look at how do you add and subtract complex numbers. Now, since they are numbers, just like 4 and pi and 7/11 are also numbers, and you can add fractions together and decimals together and all sorts of numbers together and subtract them, then there should be a way of doing the same with complex numbers. So here are two complex numbers. And normally they just put brackets around each one just to kind of emphasize that this is the first complex number and this is the second. It's quite cosmetic, at least for addition. Now, if you remove the brackets, since it's an addition, nothing changes when you do that. You get that. And then we use a rule that we've used in a lot of algebra situations. You collect like terms. So 8 add 2 gets you 10. And then you have negative 3i plus 5i, right? You collect those together. And think like x's. Negative 3x add 5x would get you plus 2x. Negative 3i plus 5i works in the same fashion, plus 2i. And there is your addition. Now let's take the same two complex numbers, but subtract them. When you subtract, nothing happens to the first term, but when you subtract, you basically pass that negative through all the terms. So you see you now have that. And you collect like terms, so 8, negative 2. So that's 8 take away 2. And then you have a 3i minus a 5i. 8 take away 2 gets you 6, and 3 take away 5 leaves you with negative 2i. And you now have that as your answer. And it's not a surprise, I hope it's not a surprise, that when you add two numbers, in this case complex numbers, the answer you get is different from when you subtract the same two. But that kind of makes sense. 5 take away 2 is not the same as 2 take away 5, right? Adding and subtraction do have different consequences when you combine them. Now let's look at some add and subtract with some special extra things going on. So 7 plus 3i add 2 take away 3i. So I'm going to, since it's an addition, I can remove the brackets, but I do not change anything. And I have a 7 plus a 2, which gives me 9. And I have a 3i, take away a 3i. And you might say, well, that means 0 i's. But we don't write 0 I, because in mathematics, 0 anything is just 0. So we don't even say it's 9 plus 0. We just say 9. So this guy, add this guy, these two complex numbers, ends up giving you just a real number 9. Now in this case, you're going to be subtracting. So nothing happens to the first complex number, but you subtract the next one. So you subtract 5 and you subtract 4i. Now when you collect the like terms together, you get 2 take away 5, which is 3. And you have positive 5i take away 4i. And again, the temptation might be, well, 5 of these take away 4 of these. That leaves me with 1i. Well, we never write 1x. We only write x if you've got one of them. And that convention still holds true. You just call that guy 3 plus I. So if you want to add or subtract fractions, I should say complex numbers, this is how you go about it. Well, how about multiplying? Multiplying causes its own little idiosyncrasies. So before I show you multiplication, I want to show you an idiosyncrasy. If I said to you, what number is I squared? The correct answer is -1. And the reason for that is that this is the square root of -1 times itself. And if you multiply a square root by itself, you should get whatever this is. So you just have to remember that I squared is the number -1. So whenever you see an I squared, you will then replace it by the number -1, the real number -1. And as long as you keep to that little extra thing, you're normally going to be totally fine. So for instance, if you were being asked, as you are in question 23, to multiply 6i by -8i, you should say, okay, 6 times -8 times I times I. All I'm doing is rearranging the order the multiplication happens in. So you should get -48i squared. And a lot of people can go from here straight to here without that bit in the middle. Right, -8 times 6, -48, I times I squared, done. Now, -48 times I squared is actually this value of it is -1. And so -48 times -1 gets you 48. So the answer to this multiplication is just 48, which might seem a little bit surprising to you, but that's exactly what you would get. Well, how about multiplication with a distributive logarithm? So like an example of that would be question 25. And in question 25, you have 2i times 8 plus 5i. Or at least a version of this. Now you're going to do distributive law. That means this guy times 8 and then this guy times 5i. So let's write that down. You're going to go 2i, I should say, times 8, and that's going to get you 16i. Then you're going to go plus, and you're going to go 2i times 5i. And 2 times 5 gets you 10, and I times I gets you I squared. So hopefully you're with me up to that point. Then I squared gets replaced by -1. Oops, so what you're going to get here is -10. And I would typically write the real number first and the imaginary part second. So there is your answer. That 2i times this ends up being that. Now, we know that I is the square root of -1. And we've just talked about the fact that I squared is a number -1. So you might think, well, what happens if you just keep going? Do you start getting weirder and weirder answers? Not really. If you wanted to know what I cubed is, what you think of it as an I squared times one more I. And I squared is -1 times one more I. And -1 times that guy is -I. So I squared is the number -1. I cubed is -I. Now, if I wanted to do I to the power of 4, which would be the next power, I could call it I squared times a second I squared, which would be -1 times another -1, and two real numbers that are both negative gives you +1. Oh, I guess I should do one more. If you're doing I to the power of 5, the easiest way to deal with it is to think of it as I to the power of 4 times one more I. That's the quickest way of dealing with I to the 5, right? 4 plus one more. I've already found out that that guy, this place here, is worth 1. So it's essentially 1 times I. And oh, And if I just call I to the power of 1, if I just call that I, do you see what happens is it just cycles through these guys and then it ends up back where it started. And then I to the 6, I to the 7, I to the 8 just ends up being either an I, a -1, a negative I, or a 1. That's the only 4 values you get, no matter how many different powers of I that you work with. So the last thing that we need to look at in multiplication, in fact, the last thing we need to look at in this section, is FOIL. Ones, if you have to multiply those two together. And the reason I said FOIL is because that's exactly how we're going to do it. It's just like 3 plus 2x, 5 to equal 5x. So you start with the F, which in this case is what, 3 times 5, which is just 2 real numbers, so you get 15. So that's the F part. If you want to do the outside, the O, you go those two. And 3 times -5i gets you -15i. Do you see? It's very like the algebra with x's. Now you want to do I, it's the inside too. And positive 2i times positive 5 gets you positive 10i. And then if you do the last, you're going to do 2i, excuse me, 2i times -5i. So I'm going to write that up as a little bubble of working. 2i times -5i. Well, that's -10i squared. But since I squared is -1, it's -10 times -1, and the answer is 10. And that's L. Now you collect like terms, so you have 15 plus 10, which gives me 25. And you have -15i plus 10i in the center, and that gets you -5i. And once you get to a step that looks like that, you know, a real part and an imaginary part, you're finished. So one more. Do a strange one. How about 5 plus 3i and 5 take away 3i? That's pretty ugly. If we do F, we get 5 times 5, which is just 25. If we do the outside, you get 5 times -3i, right? 5 multiplied by that gets you -15i. And that's the O part. Do the I and then the L. The inside is these two, and positive 3i times positive 5 gets me positive 15i. I'm keeping the last one to the end. 3i times -3i. I'll do a little bubble here. 3i times -3i is -9i squared. And since I squared is worth -1, it's -9 times -1, which is just 9. Well, if you collect the like terms, you've got a 25 here and a plus 9 here, which gets me 34. And these two guys cancel out. So you do not write 0i, you just write 34. So that complex number, right, these two complex numbers multiplied together, actually end up with just a nice real number, 34. And we are done.